Hello, my name is Eduardo Mello, and I'm going to present to you the research Dr. Peter Bauer and I have been doing on energy optimum speed trajectories in urban traffic implementation options. I'm going to present to you an introduction in problem motivation, some previous results, implementation problems, realization approaches for efficiency optimized driving, trajectory generation, and finish with the conclusion and outlook. According to the EPA, 30% of the man-made CO2 emissions come from the transportation sector. And while electric drivetrains are playing a major role from the transition from fossil fuels to greener options, electric drivetrains also offer a great potential for efficiency improvements by optimizing their speed trajectories. The confluence of electric drives, autonomous vehicles, and situational awareness allow for the optimization of the speed trajectories. And in this paper, we are going to focus on the impact caused by other traffic participants on the execution of these optimal speed trajectories, as well as the real-time computation of these optimal speed trajectories. It was previously shown that optimal speed trajectories can be achieved by minimizing the energy at the battery of a vehicle, given some constraints such as the segment length, the average speed, maximum and minimum accelerations, as well as maximum and minimum jerk, and zero boundary conditions. In the right here, you can see an example of an optimal speed trajectory, and you can see it can generate significant savings in comparison to a typically seen trajectory, in this case, a distilled version of the FTP75. However, these efficiency gains depend on the exact execution of this optimal speed trajectory, and optimal trajectories are often not possible in urban traffic. The computation also must be done in real time, and the information coming from the situational awareness of the vehicle is changing very quickly. In order to overcome these difficulties, we are suggesting a few realization approaches, the first one of them being the implementation of urban platoons. Urban platoons can be divided into rigid platoons and floating platoons, where while they are all executing optimal speed trajectories, in rigid platoons, all vehicles are executing the exact same optimal speed trajectory generated for the average vehicle in the platoon, and in floating platoons, every vehicle is executing its own optimal speed trajectory, thus the distance between vehicles vary over time. In the right here, you can see the savings obtained for a rigid homogeneous platoon with sizes varying from 2 to 20 platoon vehicles, and you can see that the savings are between 40 to 55% across the board. One important aspect of those floating platoons and also the rigid platoons are the admission rules. What vehicles can we accept in this formation? And we're going to suggest three different rules to accepting those vehicles. The first admission rule that we are going to introduce is the minimization of the total transportation energy. In this rule, if the energy consumption of the platoon plus the energy consumption of the candidate vehicle is greater than the energy consumption of that platoon united with the vehicle, then the vehicle is going to be accepted into the formation. Otherwise, the vehicle is rejected. A second rule is named specific parameter intervals, and in this rule, as the name says, we define a minimum and maximum for the parameter set of the vehicle. Like, for example, we can define vehicle parameters such as the ratio CDA over M, the rolling resistance, the maximum acceleration, and the minimum acceleration. And if the candidate vehicle has parameters that lie between those two thresholds, then the vehicle is accepted to the formation. The third and final rule is the individual vehicle voting, and in this rule, every vehicle is going to analyze its energy consumption with and without that candidate vehicle in the formation. If most of the vehicles observe savings with the union of that vehicle with the platoon, then the vehicle is accepted in the formation. Otherwise, the vehicle is rejected. The next realization I would like to introduce is the piecewise linear trajectory approximation. And in this case, we are approximating a scenario seen in a typical traffic. In this case, the curve in blue is extracted from the FTP75 by a succession of segments of hard acceleration followed by segments of coasting. And in this scenario is particularly useful for dense traffic where you cannot allow much distance between vehicles. And the coasting deceleration is calculated by the equation shown on the left here, while the deviations from the typical trajectory to our piecewise linear approximation is limited by the variable here defined as delta Vmax, and it's a constant over the entire trajectory. The distance between the vehicles shown in the middle here is then given by the difference in the integral of the speed of each one of the vehicles. Utilizing this piecewise linear approximation of the typical trajectories into the entire FTP75 and average every segment into the trajectory, we get the savings shown in the blue bars here in this plot. And the red bars represent the overall savings of the entire FTP75. And as you can see, as we increase delta Vmax, our energy savings increase. But you have to remember that by increasing delta Vmax, we also increase the distance between the minimum distance between vehicles, and thus making this trajectory harder to realize in dense traffic. The third realization approach that I would like to introduce is the low-pass filtering of the optimal speed trajectories. In this case, if you think about convolving the optimal speed trajectory with an impulse response that is positive and has a DC gain of 1, we did not change the travel distance by the vehicle, and we only slightly changed the average speed based on the duration of that filter. And also, we can think about delaying that execution of that optimal speed trajectory, and if you think about that, does not change the energy consumption of the optimal speed trajectory if you're assuming zero parasitic power, and is still able to increase the distance between vehicles. The images on your left here show an optimal speed trajectory and its filtered counterpart. And as you can see, the orange line is much more smooth than the blue one, and thus we were able to reduce the onset on both acceleration and jerk while obtaining minimal energy changes between the two trajectories. And the only significant difference between the two is that the trajectory has its duration increased by the length of the filter. On the right, you have a plot that shows the distance between the lead vehicle that's executing a typical trajectory based on FTP75 and the optimized trajectory, and a second vehicle executing the optimized trajectory. And as you can see, the optimal trajectory requires a large distance between the optimized vehicle and the lead vehicle. When we filter that trajectory, that distance between the two vehicles is greatly reduced, but still not within a reasonable threshold. When then we further insert a delay in that trajectory, then we are able to maintain the distance between the two vehicles in an acceptable range, and in this case it's stipulated to be 5 meters. The last approach that I would like to introduce is lowering the maximum acceleration, and that can significantly increase the feasibility of these optimal speed trajectories because the distance between the vehicles is going to be maintained for a longer period of time. Typical traffic accelerations are between 1.5 and 2.2 meters per second squared, but as we can see in the plot on the right, if we reduce these maximum accelerations, we significantly decrease the savings obtained by the optimal speed trajectories. Diminishing returns are seen if we increase the maximum acceleration above 4 meters per second, and that suggests that we would like to stay within the right side of this plot shown. In addition to the execution of these optimal speed trajectories, we have to think about the real-time generation of these trajectories. And one way to work around the real-time calculation of these trajectories is storing a pre-computed data set of possible optimal speed trajectories. Knowing that optimal trajectories have between 50 and 300 data points, and assuming the upper bound of 300 data points, we can quantize distance segments in intervals of 10 meters, for example, and average speeds in increments of 1 meter per second. And if we assume the segment lengths optimized vary between 100 meters and 3,000 meters, and that our average speeds vary from 3 meters per second to 23 meters per second, we only get 6,000 trajectories. We can also consider that the maximum allowed acceleration and deceleration can vary depending on the trajectory that you're trying to optimize. And if you consider a combination of 16 of those, we arrive at 384,000 trajectories. To start all those trajectories, it only takes 220 megabytes of storage if we're storing them as 16-bit integers. While that space requirement is not very big, we can further reduce the space requirement by using a using a compression algorithm, like for example the Huffman coding, and that can reduce our storage necessary by approximately a factor of 10. Another option is to only store the critical points of those optimum speed trajectories and not the entire trajectory. For example, on the image shown below here, this optimum speed trajectory can be closely approximated by only using 3 data points, and each point being a pair of data, the time and speed. If you think about these 384,000 trajectories, each one being necessary an average of 10 points to fully describe, and each point being 4 bytes, we only would need around 15 megabytes of storage to store all these 384,000 trajectories. Another option is, instead of calculating the optimum speed trajectories, we can calculate closed form approximation of these optimum speed trajectories. For short segments, as it's shown on the right here, we can subdivide these optimum speed trajectories into 3 linear segments. And the distance is given by the distance traveled by the vehicle is given by the integral of that plot on the right. And the total time is given by the distance and the average speed. Based on these equations, we can obtain a system of equations to calculate the quantities T1, T2, T3, and A2. And we can also estimate the energy of the battery, if we assume no regenerative braking, by the equation shown at the bottom here. If we utilize the closed form approximation shown in the optimum speed trajectory for segments varying from 300 and 800 meters, we obtain the graph shown below here. And as you can see, the bars in blue represent the estimated energy consumption for each one of the trajectories based on the closed form approximation. Utilizing that closed form approximation generated and actually computing the energy consumption of the trajectory, we obtain the bars in orange. And the bars in yellow represent the actual optimum speed trajectory generated for each one of these trajectories. You can see the closed form approximation utilizes a little less energy than the optimum speed trajectory. And that is the case because while they strictly follow all the constraints posed in the optimization problem, the closed form approximation does not. And each one of these trajectories represents significant savings in comparison to the distilled version of the FTP75. This research aims to facilitate execution of these optimum speed trajectories by trajectory implementation, modification, and the adaptation of these trajectories to traffic conditions, as well as trying to increase the computability in the real-time trajectory generation of these optimum speed trajectories. While all the investigated approaches are effective, urban platoons, pre-computed speed trajectories, and closed form approximations of the trajectories are the most promising aspects. Thank you for watching this presentation.